light. So this one is related to refraction of the light. And the first 5 questions from 6 questions are recorded. So we'll start with question 7. This one is all about refraction, as all the questions from refraction are there. So question 6 is done. Question 7, I'll start with. In this question, we have a dishwashing machine using a solution known as a rinse aid to prevent the water from leaving the mark on the dish as they dry. A student carries out an experiment to determine the refractive index of a rinse aid. The photograph shows a ray of a light passing through a rectangular container, as you can see here. It's passing through a rectangular container of a rinse aid. The container is having a rinse aid. Take a measurement from a photograph to determine the refractive index. You must record your measurement. You may ignore any effect from the container. So what we have to do, we need a refractive index. So what you have to do in exam, like, because you have to use a figure. So this is a surface, so you will draw the normal. And after drawing the normal, measure using a protractor, measure this angle. Like example, this is θ1 and this one is θ2. This is a refractive index of medium 1, N1. Refractive index of a medium is N2. So you will use a Snell's law, N1 sine θ1 equals N2 sine θ2. So N1 is the air, so refractive index of a air is equals to 1. What about θ2? So you have to measure using a protractor, you have to measure this angle. So it has to be done with measurements. And θ2 also you have to measure this angle. After like measuring, and because repetition is always important, like you cannot just find the values, accurate values with one set of results. So you should always repeat. So how you can repeat? So you can see the other set of results are there. That is when it is leaving. So this part is also there. So for this part, you will have angle like this will be θ1, this will be θ2. You have to measure these angles. Now the refractive index of this medium is N1, which is called N. And in here the refractive index was N2 because it was moving from air to glass, air to the rinse aid, and now it is moving from a rinse aid to the air. So the refractive index of a medium 2 will be 1. And again use the same formula. Again use the same formula, N1 sine θ1 equals N2 sine θ2. So this has to be done with the measurement. First, you will measure from this side, then you will measure from the other side. And then what you have to do, you have to take an average. That will give you the refractive index of this rinse aid. So example, say this angle, when it is moving, I'm just taking a values. Say this angle was 52 and this angle was 34. So when we use N1 sine θ1, so sine 54 equals N2 and sine θ2, which is 34. So we need the refractive index. So refractive index will be sine 54 over sine 34. What's the answer? If you take sine 54 over 34 degrees, keep in mind theta should always be in radian. So 1.46. Always write your answer in two significant figure or three significant figure or two decimal places. So measurement and calculation that you will show. Now in the second part, the rinse aid is stored in a small reservoir in a dishwasher with an optical dipstick to indicate the level of the liquid. The dipstick is a clear plastic cylinder with a pointed end that dips into the liquid. I think the image is given here. Yeah. So these are the appearance from above when empty is there. That is how it looks like. But when appearance from above when it is full, that's how it looks like. Now, the dipstick is a clear plastic cylinder with a pointed ends that dips into a liquid, shows that the critical angle for a light in the plastic when surrounded by the rinse aid is about 60 degrees. The speed of a light in rinse, so here what is happening? The light is moving from rinse aid to a plastic or from plastic to a rinse aid. So you don't have a refractive index 1 here. You have to show the critical angle, and look, this is 2.22. The speed of a light in a rinse aid and the speed of a light in a plastic is 2 exponent 8. So means the speed of a light in a plastic is much smaller. So means the plastic is having a higher refractive index than the rinse aid. So whenever critical angle is there, it is moving from denser to rarer. Because for a critical angle, when a light travel from denser to rarer, it will bend away from the normal and the angle of a refraction will be 90 degrees. So in this case, the light is moving from plastic to the rinse aid. We need this angle. So how we can work out? We have the formula N1 V1 equals N2 V2. Speed in a medium one. So first using this, and the other formula is N1 sine theta 1 is equals to N2 sine theta 2. So first what we will do, we will first find the speed. First we'll find the refractive, and we have the refractive index of the rinse aid. That is in the part A we calculated. For our value it was like 1.44. So according to the calculation, the answer from the previous part. First we'll find the refractive index of the plastic, and after finding the refractive index of the plastic, we'll have the refractive index of the plastic. We will find this angle, and the angle of refraction will be 90 in the rinse aid, and this will be the refractive index of the rinse aid. So N1, the refractive index, like any one of the side you can take. Like example, if I'm taking this side as a plastic, the other side will be a rinse aid. So refractive index in a plastic, we don't know. The speed in a plastic is 2 exponent 8. The refractive index of a rinse aid, that is our previous answer, like 1.44 or 1. The actual answer should be 1.34 according to the last value. So example, we are taking 1.34, and the speed, that is 2.2 into 10 to the power 8. Now we need a refractive index. So 1.34 multiplied by 2.2 into 10 to the power 8 divided by 2 into 10 to the power 8. So we get the refractive index 1.48. And it is obvious that the plastic should have a higher refractive index because the light is traveling slower. So we got a refractive index. Now we use this formula, refractive index of the plastic, which is 1.48. Sine theta 1 is what we are finding because it is moving from because to be for a critical angle, it should travel from denser to rarer medium. So this will be theta. Refractive index of the rinse aid is how much? What's the value? It was 1.34. And what is the angle of refraction? 90. So if I need this theta, so sine theta, so when we simplify, we get theta is 64. So about 64 degrees we'll get. So we have to show it is about 60. So it is closer to 60 and that is correct. Is it clear, this question? The next is the photograph below shows a difference between the appearance of a dipstick when the reservoir is empty and when the reservoir is full. When the reservoir is empty, the dipstick is surrounded by air and it appears that the light, because the light from the surrounding is reflected back into the viewer. When the reservoir is full, the dipstick is surrounded by a rinse and it appears dark. Like this is when we are looking from the top. Okay. So when we are looking from the top and it is empty, we are able to see the light. But when it is filled with the, like when the dipstick is surrounded by the rinse aid, it appears dark. What is the reason? Look, what actually happened? It's like we are looking from here, the top. Like our eye is here on this. It's like you imagine you're looking something from the top. So your eye is at this point. So when we are looking from here, how this will appear a light, because the light will reflect, like undergo, this is moving from plastic to air, this angle of the incidence is more than the critical, so light will undergo total reflection and then again total reflection and enter the eye. That's why it appeared to be that light appear. But what will happen here in this case, when a light is moving from air like plastic to rinse aid, when it is filled with a rinse aid, refraction will happen, but it will not undergo total reflection. So as a result, no light returned back to us. So as no light appear returned back to us, so what it will appear? It will appear dark. And here, what it will, how it will appear? It will appear bright. Is it clear? The two figures. Why one appear to be brighter, and other one? Why one we are able to see the light, the other one? This is a dipstick. The dipstick, when the tank is empty, it is surrounded by air. When it is surrounded by air, when the light strike, the light will undergo total reflection and it return back. So when it return back, you will see the light. It appears that it is brighter. But when it is filled with the rinse aid, the dipstick, and surrounded by the rinse aid is having a greater density than the air, so then the refraction will happen for a light, because this angle is not equal to a critical angle, because this angle should be 60 degrees, but it is obvious it is not 60 degree, it is less than 60. So a light will undergo simple refraction, so we won't be able to see any light is reflected, like the light from outside going inside and then reflected back to us, so it will appear dark. Complete the diagram to show the path of a light when the rinse level is low. Critical angle for the plastic surround, like here, if you see, the critical angle is 42. So when we draw the normal and you measure this angle, this will be more than 42. So light will undergo total reflection. When you draw the normal, this angle will be more than 42. So it will undergo total. But when you draw the normal here, because this angle, the critical angle for a plastic to rinse aid must be 60 degrees. The critical angle is 60 or 64, what we calculated. But when you measure this angle, it won't be 64. It will be around 46, 45. So it will undergo a simple refraction. In question 8, a water waves approaches a boundary between a deep and to a shallow. And the diagram shows how a direction of a travel of a wave changes, angle of incidence and refraction are mentioned. Explain why the wave is refracted as shown. From a deep water to a shallow, you may draw a diagram. So what will happen? Why in a refraction, the speed changes. So what happened when it travels from deep to shallow? The speed decreases. When the speed decreases, the part of a wavefront which meets the boundary, they will slow down. So we can draw on the diagram, like you may add to a diagram. So how we can add to a diagram? If you draw the wavefronts, so the part of the wavefronts which are in a deep, they are moving faster. But the part of wavefront which are in a shallow, they are moving slower. So they will lag behind. So as they lag behind, it will bend towards the normal. So answer here, the point you will mention, one point, that there will be the speed will decrease, you will mention that. And the second point, the wavefronts, which the part of a wavefront which meets the boundary, they bend towards the normal, or the wave will slow down. If the speed increases, it will bend away from the normal. When the wave travel across the surface of a water, their speed v is dependent on the depth and the wavelength. For a wave traveling in a deep water, where d is greater than half of wavelength, so this is the formula for speed. And wave traveling in a shallow water, v is equals to under root gd. Calculate the angle of the refraction. The wavelength of a wave in a deep water is given to us, depth is given, depth of a shallow is given, and angle of incidence given. So we have to use two formulas here. One is, first we need the speeds, and we need a refractive index of the mediums as well. Like this is a formula which will give us the speed. This is a formula which will give us the speed in a deep. V is equals to under root g lambda over 2 pi. So the formula which will give us the speed, this is a formula which will give us the speed in a deep water. Okay. Gravity is there, lambda is there, 2 pi. So we got this speed. You can say this as V1. Then V is equals to under root GD. Using a depth, you will get the speed 2. Then you will use a formula N1, and the other values, the angle of incidence is given. As you can see, angle of incidence is there. We need angle of refraction. So we can also compare the angles. We have the formula N1 V1 is equals to N2 V2. Or we can also say N1 over N2 is equals to V2 over V1. This is one formula. And there's also another formula, N1 sine theta 1 is equals to N2 sine theta 2. So if we simplify this formula, N1 over N2 is equals to sine theta 2 over sine theta 1. So if I compare these two formulas, I can also have a relation between the speeds and the angle. So it will be V2 over V1 is equals to sine theta 2 over sine theta 1. So any one of them, you can say, like example, if a deep, you're saying V1, so this will be the speed in deep water. This will be the speed in a shallow water. The angle given in the deep water is there, the angle of the incidence. So you can work out the angle in the shallow water. Is it clear how to do this question? As the values are given, we just have to substitute and work out the ratios. So using this formula, you will get the speed in a deep water. With this is V1. Using this formula, you will get the speed in a shallow water. And we know the refractive index into speed is equals to refractive index of the second medium into speed. So the ratio of the refractive index is reciprocal to a ratio of the speed. And in terms of angle, N1 sine theta 1 equals N2 sine theta 2. So the ratio of the refractive index is equals to sine theta 2 over sine theta 1. So if we compare this equation with this equation, so we can say V2 over V1. This is V1, we'll have here. This is V2, we'll have here. The theta 1 is given in the question, as you can see. The angle of the incidence is given in the question, which is 40. So you can work out the angle of refraction. In 1933, the crew of US Navy ship USS Rampo took a measurement from one of the largest wave ever recorded. The wavelength of a wave was 342 meters and the time period was 14.8 seconds, show that the depth of a water where the crew measured the wave was greater than 170 meters. So how we can show that the depth where they took this measurement was more than 170 meters? So first we'll work out the speed. How we can work out the speed? We have the time period. Time period is reciprocal of the frequency. So we'll use the formula V is equals to F lambda. This is a wavelength and this is a time period. So if we need the frequency, frequency will be reciprocal of the time period. So speed is equals to 1 over T into lambda. So 1 over 14.8 multiplied by wavelength lambda, which is 342. We will get the speed of this wave in a deep water, which will be 23 meter per second. Okay. 23.1. Okay. So this is 23.1. Now, how to work out the speed in a the formula, which if you see, this is given in the beginning. You don't have to memorize this formula. So the formula of a wave, speed of a wave in a deep water is given by this. Where the depth, where D is the depth and it should be greater than half of wavelength. So we'll use this formula. As this formula is given in the question. So we use V is equals to under root G lambda over 2 pi. And using this formula, if we work out the speed, so this is 9.81, the wavelength is 342, and 2 and the pi is 3.14. So what we will get? We'll get again 23.1 meter per second. Now, what is the condition for this formula? Like we're getting the speed as 23, like same speed we're getting. First, we confirm that it is holding the relation. And now, if you see the mention, this formula where D is equals to D should be greater than half of wavelength. So if D should be greater than half of wavelength, so D should be greater than 342 over 2. And 342, because the wavelength was 342. So 342 divided by 2. We'll get 171 meter. So means as we are getting the speed 23.1 meter per second in a deep water, so the depth of the deep water should be more than once, because this condition is given here in the beginning of the question, that when a wave traveling in a deep water, the depth should be greater than half of the wavelength. So if wavelength is 342, 342 divided by 2 means 171 meter. And when we get 171 meter, what it shows that the depth in which this deep water was, like the water was traveling, that was more than 171 meters. and that is what we have to show that the depth of the water where they measure, that should be more than 171. So first we find the speed by using a formula v is equals to f lambda, and then the formula which is given. Both formulas are giving the same speed. It means that this should follow a relation that the depth in which this wave was measured, that was greater than half of the wavelength. Is it clear, the last part?